Welcome everyone to another segment of supplementary videos, and today we will be discussing about the various ways of writing the different vector fields in various kinds of coordinate systems. So in the previous segment we introduced the various types of coordinate systems, okay, and the volume elements in the respective coordinate systems. Okay, so today we will be starting and try to build a framework to write the various vector fields in a generic coordinate system. Okay, so let's start. So what we'll do is let's assume we have an general curvilinear, or let's say orthogonal curvilinear coordinate system to begin with. In 2 dimensions, the coordinate systems could look something like this. This is any arbitrary, and then we can also have the third dimension. So that's the generic coordinate system that we are thinking about. So this is the 2D in 2D. So in 3D, any generic coordinate. So in 2D, the isolines, as you can see, are represented by curves. So these are the isolines. So let's call in 3D the general coordinates are represented by u1, u2, and u3. Those are the 3 orthogonal directions in the curvilinear coordinates. So u1 equals a constant, u2 equals constant. So these curves in 2D represent these curved lines, these constraint relationship, and in 3D this will require curved planes. So these, a set of these 3 system of equations defines all the iso surfaces basically in that coordinate system. Okay, so here C1, C2, and C3 are constants. So if you take each of these, let's say this and this, or this and this, they will intersect at a curved they will intersect at a at a curve basically, like so. So it's like so we have, this is one surface, and then we have some other surface. So the intersection of this is basically a curve in general. Okay, so and these two surfaces are represented by one of these constraint relationships. Okay, and one important thing that we need to be kept in mind is, since we want to work in only in orthogonal coordinates, that means this the iso lines or the iso surfaces always intersects at right angle wherever possible. Okay, so this all are 90 degrees. It doesn't look like 90, but these are 90 degrees. Okay, so that's what we mean by orthogonal curvilinear. So here also at the point of intersection, it intersects at right angles. Okay, so let's say we now have any general vector. R is a position vector. Okay, and in Cartesian coordinates, the R is the components of R is given by x, y, and z, correct? So let's say uh, we want to find out a relationship between, let's say, how between let's say we want to represent a single point in both Cartesian coordinates as well as, let's say, in this curvilinear coordinates. That means we are seeking relationship of short x equals x some function of u1 u2 u3, where u1 u2 u3 is the new curvilinear coordinate, y is function of u1 u2 u3, and similarly z is a function of u1 u2 and u3. Okay, that's a generic relationship. That so these things so these are basically equations of the form when we were discussing coordinate systems and we were discussing the transformation rule. So something like this basically. So that's a generic, so we are trying to write the generic form of these set of rules, okay, the coordinates that we did before. Okay, so it's something like this, from Cartesian to cylindrical, from Cartesian to spherical. So the general transformation rules are written in this way here. Okay, so that's the generic way we want to seek a relationship of that form. So so in Cartesian, this R is given by x I cap plus y j cap plus z k cap, where the I j k denotes the unit vector in the x, y, and z direction. So this is I, j, and in this direction we have k. Okay. Okay, so now, so let's see how we will do it here. So what we want to do is try to represent any generic arbitrary vector R in this curvilinear coordinates. Okay, so that's our task at hand. So what we want to do is, so let's say we want to represent the position vector in curvilinear coordinates. Okay, in curvilinear coordinate system. Okay, and what we will do is we will and this could be done in two ways, and those form two different systems. Okay, so this representation, there are, we can use, presentation can be done by using the tangential components or by the normal components. And tangential and normal, what we mean, we will discuss now. What do we mean by those things? So whenever we represent a vector in this curvilinear coordinates in terms of the tangential basis, or tangential basis instead of components, let's write basis, tangential basis, normal basis. Okay. So when we do it in tangential basis, this is known as contravariant basis, and when we do it in the normal basis, that is known as the covariant. Okay, the covariant basis. So let's say we have a vector, let's say R, at a point P, and at that point P, let's say we have some isosurface. This is point P, and this is the isosurface, let's say, given by u1 equals c1. Okay, so this is, let me draw this as in different color. This is the u1 equals c1. Okay, and on top of that we have the point P. Okay, so you see at point P we can define a tangent to a tangent plane basically. So this is a tangent plane. This is the tangent plane at P to u1 equals c1. Similarly, we can define another direction, which is the normal direction. This is the normal direction. This is normal direction to u1 equals c1. Okay. That means let's see how we can write a tangent vector at point P. So any tangent vector at point P will be in this direction. Okay, so the tangent vector at P, okay, at P to the surface, or let's to the surface u1 equals c1 is given by partial r partial u1. Okay, and this is the tangent vector in this direction, and in that direction let's call the unit vector to be e1 in this direction. In this direction, the unit vector we are calling, let's say, e by e1 hat. Okay, so e1 hat, so this is the vector, this is the tangent vector. So the unit vector in that tangential direction is e1 hat, which is del r del u1 divided by its magnitude, which is del r del u1. So this we can write in a different way, in which we have del r del u1 is equal to partial r partial u1 magnitude times the unit vector. Okay, and this we can write in this, which is rewrite h1 e1, where we call this, see, this is just a scalar, this is known as a scale factor, and that is partial r partial u1 magnitude, that is h1. Okay, similarly we can write in the other two directions del r del u2 is h2 e2. Okay, where h2 is the magnitude of partial r by partial u2. Okay, and partial r partial u3 is h3 e3, where h3 is the magnitude of partial r partial u3. Okay, so in a generic index notation we can write this, all these three equations, as del r del u I is equal to hi ei cap, where hi is the magnitude of partial r partial ui, the scale factor, the generic scale factor. Okay, so that's the representation, that's the, you can think about these e's, e sub I cap, these represents the contravariant basis. Okay, so now let's do the let's try to represent in terms of the normal. Okay, so at P, the normal, so at point P, the normal vector to the surface u1 equals c1 is given by the gradient, okay, that we know. So this, in this direction, basically the normal direction, we will have the gradient, that is the direction of the gradient u1. Okay, so in the normal direction, the unit vector, let's call that capital E, one cap, and let's write that as gradient of u divided by the magnitude of u. Okay, that's E1. So like that, in a similar fashion, we can write the generic components, which are given by EI at is grad u divided by the, or let's grad ui, because this will be u1 basically. So this is normal to the curve u, or surface u1 equals c1. So this is e, therefore e1 should be grad u1 basically. This is u1. Okay, so grad ui divided by the magnitude of grad ui. So that's, these are the covariant basis vectors. Okay, and in general, what happens is, in general, the contravariant and the covariant systems are reciprocal. Okay, that means that, so the generic, which is the generic tangent vector. Okay, and if you take the dot product of this tangent vector with the contravariant is uj, this in general is the Kronecker delta. Okay, this is the Kronecker delta, where delta ij equals 1 if I equals j, and this is equal to 0 if I is not equal to j. Okay, so that's the relationship between, let's say you can think about the contravariant with the covariant basis. Okay, they form some kind of a reciprocal systems to each other. Okay, so let's say a differential element dr vector in the curvilinear coordinate could be represented something like this, where remember r is a function of u1, u2 and u3. So I can write this as u1 du1 plus partial r partial u2 du2, and then we have partial r partial u3 du3. Okay, and therefore we can write this in a little bit different way, which is using the summation notation. It will become sum over partial r partial ui dui, where I goes from 1 to 3. Okay, and let's take the gradient of u1, and from our earlier studies of vector calculus we know grad u1 dot dr1 is nothing but, or let's say grad u1 dot dr is du1. That's from where the idea of that at u1 equals constant, grad u gives the normal direction. Okay, so if we write this product grad u1 dot dr, this is du1, and this could be written using the summation we already have, which is grad ui dot partial r partial ui dui. Okay, and I goes from 1 to 3, from 1 to 3. Okay, so that's how we get the dot product of these two systems. If you see, since only the dot products in the same direction will survive, we will have grad u1 dot partial r partial u1, that has to be 1. Okay, on the other hand, grad u1 dot r partial u3 equals 0, and grad u1 dot partial r partial u2 is also 0. Okay. So let's write any arbitrary gradient of any, let's say, function p, that could be written in terms of the contravariant components as sum I equals 1 to 3 f sub I ei hat, and the dr vector similarly could be written as partial r partial u sub I times dui sum over I equals 1 to 3, and this could be written using the scale factors I equals 1 to 3. Partial r partial ui can be written as hi ei cap, so that is using the definition of scale factors, if you remember where we were writing this. So this, using this expression, partial r partial ui is hi ei cap. That's what we are doing. Partial I partial ui is hi ei cap. This becomes dui. Okay. And so this is the grad phi, this is dr, and if we take the dot product of the two, grad phi dot dr, we will get the elementary change in phi, so that is d phi. D phi is grad phi dot dr, and that is equal to sum over I equals 1 to 3 hi fi dui. Okay, and that is the same as summation of partial phi partial ui dui, in because you remember phi can be represented in terms of the curvilinear coordinates u1 u2 u3. If you see from here, we get a very interesting and useful identity between the scale factors. So this becomes hi. Fi is partial v partial ui, or fi is 1 over hi partial v partial ui partial v partial ui. Okay, so let's write the grad of phi. Grad of phi was the fi is for that's we found out what phi is. You see, we can use that thing here. Grad of phi is sum over I equals 1 to 3 ei hat by hi partial phi partial ui. Okay, so that's a way of writing grad phi. And if you see from here, we can write a generic version of the gradient operator using the scale factor and the contravariant basis. That is, so the grad, this the del operator basically. So this is the del operator. Del operator could be written in a generic way, which is sum from 1 to 3 ei cap by hi partial partial ui. Okay, that's the generic definition of the del operator using the scale factors and ei cap. Okay, in Cartesian coordinates, as we saw before, we'll have h1 h2 h3, all the scale factors goes to unity, and hence the individual contravariant basis vectors are the unit vectors in the x, y, and z directions. E2 is j and E3 is k. Okay, so as ijk satisfies the rules of the cyclic rules in cross product, same as applicable for E1, E2, and E3. Okay, that means we'll have E1 cross E2, that will have E3. Similarly, we will have E2 cross E3, that is E1. And finally, we will have E3 cross E1. So 3, 2, 3, 1, and then we'll have 1, 2 cross 3. E2 cross E3, and that is E2, we already have it. 2, 3, 1. This will be 3, 3 E1, and that is E2. Okay, so that is all about the cyclic behavior of the contravariant basis vectors. So that is for this segment. We will pick up from here in the next segment. Thank you.